plenary talk of this session going to be given by Professor Stefan Maier. So he's currently, he has a double appointment, so he's the head of the School of Physics and Astronomy at Monash University in Melbourne. He's also the Lee Lucas Chair in Experimental Physics at Imperial College. So if you are from the nanophotonics field, you would have no need to be, let's say, to have an introduction about Stefan. He has been contributing immensely to the field of nanophotonics, of nanomaterials, metamaterials. So he has been touching many different aspects of it, all the way from bio, energy, and let's say all kind of enhanced matter interaction with nanostructures. So today we're going to talk about plasmonics and dielectric nanostructures for enhanced energy harvesting, emission control, and nanometrology. Stefan.
Okay, thanks a lot, Romain, for the kind introduction. Is the microphone working, I hope? And yeah, thanks to the organizers, to Frank, for the invitation. So what I want to talk about today is how can we use nanostructures, so nanostructured materials, if I get my pointer to work, to confine light into very small spaces with one of the obvious applications that's hopefully of interest here is that this way we can build optical sensors or use these materials for efficient conversion of energy from the photon fields or from electromagnetic radiation, right? And probably quite a lot of you here will be familiar with some of the basic concepts here, right? So we use metallic nanostructures where we use plasmon resonances to generate very tight light spots around these materials. If we excite them at the right resonances, the whole thing also works with dielectric nanostructures. But the question is, are there any kind of guiding principles to actually make the focusing of light, so the absolute intensity that you get into these small spaces, efficient? And that's what I want to focus about today. And for that we use the concept of a metasurface. So we take these little structures that have field enhancement around them, and we basically arrange them on a grid. And then you not only have the response of these highly enhanced near fields that we want to use for sensors or for energy conversion, but you now also have an overall response, because if the pitch between all of these elements here, as you see in this rendering now, is smaller than the wavelength, then you don't have diffraction, but each of these nanostructures now interacts with the light field, right, with the photons that impinge on it and scatters them. Right? So with scattering, I mean it changes the amplitude, and it also changes the phase. And this, then you can basically use this, and this is now the concept of a metasurface to basically almost control waves, plane waves coming in and hitting this interface with these nanostructures almost at will. Because each of these little units now, basically, if we think back to our basic electromagnetism, how we all learned about Snell's law, right? Each of these now basically is a launching point of a spherical surface wave. And then, depending on the shape of these nanostructures, if I vary them along the surface, I can build up a quite complex phase profile on the other side of my interface. And such metasurfaces have been used this way to make lenses, to build focal points of light, to steer energy, in the wrong direction for cloaking. Maybe some of you will have heard about this. But you can actually also use this response of changing the scattering amplitude and the phase of the light as it hits the surface to make the energy focusing process into these hotspots of light very efficient. Okay, and this is a very general concept that I want to focus on today, which is called critical coupling, which basically means we try to match the strength of the way that we couple to this metasurface, to the absorption rate that we have in our material structures, and I will show you a couple of examples that this way we get the maximum amount of energy transferred into this small little spot. Okay, so in order to do that, we need a system, and this is kind of the most complicated physics here. So I will explain it in a very simplified form, where we can control very well what's the radiative coupling strength of a plane wave coming from the outside to the surface here, okay? And the basic idea is as follows. So you choose a structure that has a so-called dark mode. So like a dark mode is a mode without a dipole moment, a like mode that basically doesn't couple to the outside at all, okay? And like the most simple structure is you not only take one bar, you take two bars, like this, okay? And you are in a spectral range where you have an antisymmetric mode there. So basically you have dipole moment in this bar going up, dipole moment in this bar going down, the two cancel each other. This way you have a surface that doesn't interact with light at all. And now you break the like symmetry, like tiny bit, okay? For like example, simply by like tilting these two structures here, okay? So now our dipoles that were antiparallel before and are not completely antiparallel anymore, you now have like a tiny amount of dipole moment, and then your electromagnetic wave can couple to these structures, and you start to confine light around them, okay? And then you can basically now control the strength of this coupling by changing this angle, yeah? So you need to break the symmetry a little bit, and this way you have a mode that previously didn't couple at all. Yeah, this is called a bound state in the continuum mode. So for the specialists here, there's a little bit of hand wavy explanation that I give here, but I think for the general purpose of the message that I want to get across, that's probably fine. So you like have a flat like spectrum. The structures don't interact at all. And then you break the like symmetry like a little bit and a little bit more, and you see here at first very sharp resonance opening up. So like a very high quality factor, since you only have a very small dipole moment for a small amount of like symmetry breaking. And then as you increase your angle more and more, you like see the mode goes broader and gets broader and broader and broader. Like it also shifts a little bit. You can correct for that by like a simple like size scaling, yeah? So you now have like a very good handle via this like very like simple concept of basically saying how much does your nanostructure interact with the outside. Okay, and like the nanostructure can be like a nanostructure that you want to use for like sensing, that you want to use for energy conversion, whatever. And like the interesting part now is like following. So like there's like a very general concept in waveguide theory that says if you in waveguide and resonator theory, saying that if you want to couple the maximum amount of energy into a resonator, then you need to match its coupling constant, yeah? So the coupling constant to the outside to the internal absorption rate of that resonator. And if you do that, then you are able to transfer the maximum amount of energy from the far field to the resonator. And we now have like a very nice handle via this like very like simple like concept here to actually do that. Since we can change our coupling constant, yeah, the like sharpness of this mode, simply via a change in angle. And I want to give you now like a couple of examples where like this can be employed. I will discuss this, which is our highlight result, in like much more detail later. But like this is basically now a like surface, such as the one that I've just shown, a like nanostructure surface with these symmetry broken ellipses, and at the same time we are also able to change the absorption loss, so the material extinction of these resonators as well. Okay, and like if we then plot the material extinction coefficient versus the tilting angle, which is our radiative coupling to the outside, we can get into these conditions of critical coupling. And I will show you like a little bit later that exactly at these conditions we indeed get the maximum amount of energy transferred. So the talk is broken into like these like three parts. It's basically three different applications of this critical coupling process. Okay, and I will start with like a very, very like simple one actually, like just to show that this concept of critical coupling is actually at work in many, many different applications. And that's simply an like explanation of the colors that we get if we have a surface and we just put a very random array of metal colloids on them. Okay, so can actually also be dielectric colloids. So like really any sort of like nanostructures. And we randomize them, okay, so like they can change in size. We like just do like a sloppy, random, very random coating. Yeah. So what's the color of such a coating? Any guess? Usually, if you have a completely random structure, or like if you think about a very rough surface, roughened silicon, for example. Gray. Yeah, gray. Usually, actually, in like the limit of complete randomness, it would actually be black. And like the reason is that if you have a completely disordered structure, so basically a chaotic system, yeah, then it's a very general concept that in like such a system, actually the lifetime of each of the modes that such a highly random system can have converges actually to the same value. Okay, so like mode means here color, right? So like my chaotic system can have, you know, a mode that's in the green, that's in the red, that's in the yellow, and they all have the same intrinsic absorption if you have a completely chaotic system, meaning that if you play now with this critical coupling, you will excite each mode in with the same strength, okay? Because all of your modes have the same intrinsic loss if you have a highly disordered system. So if you couple now light to it and you are at the critical coupling condition, you will excite each of these modes with the same strength. Yeah? So you have a flat absorption. Okay? So your system will look black. Okay? And like you can actually really nicely demonstrate this if you now have a handle to change the intrinsic absorption of one of these modes, okay, of one of these disordered modes. And the most easiest way to do that is actually now not to take a simple flat surface, but you take a surface where you have a small dielectric spacer layer so that you have a Fabry-Peyroux cavity underneath, okay? Because for the mode that this cavity is tuned to now, let's say the mode in the green, means that you now influence the intrinsic damping of the green mode of this very disordered structure. Okay? So all of the other modes have still the same damping. The green mode, you change the damping a little bit, so you take it now out of the condition of critical coupling, so you couple less to the green mode, meaning the green mode will be reflected and your system looks suddenly green. Okay? So this is quite this is extremely simple physics here, but this is quite counterintuitive, because if you have a normal Fabry-Peyroux cavity, right, and you tune it to green, green gets either absorbed more in the cavity or stored more. Here it gets reflected more, simply because you play with this critical coupling condition. Green is now the one mode that you don't couple well anymore. Yeah, and you can very easily show this. So you take a deposition of silver particles, for example. Okay, you put them on a Fabry-Peyroux cavity, and then depending on the thickness of the cavity, the mode that it corresponds to, suddenly all of these bright colors start to appear. Yeah? So if you do this in a wedge-shaped structure, you can nicely see here the first order Fabry-Peyroux resonance, second order Fabry-Peyroux resonance. You know, and then you can use this as a very simple way for generating color, for example. So you take an image, you simply emboss it. Okay, in terms of small different thicknesses. So each thickness here corresponds to the color that we want, and then you do one big and quick deposition of silver colloids on it, and you get that color. Okay. I should also say one really interesting aspect here is, because this only depends on disorder and on critical coupling, the actual material doesn't matter at all. So these colloids can be whatever they want. It won't influence the color, right? So we all know, of course, that if we have a simple, single colloid, which I just show here for the plasmonics people around you, gold, silver, platinum, and palladium, and we use Mie theory to calculate the color where this particle scatters, the most obviously they are very different, right? They depend very much on the material. So if you now would make a regular array of these colloids on a surface, yeah, the color that you get would also be completely dominated by the material's response. But if you go to a disordered surface, yeah, and then again, this concept of that all of these modes will start to have the same intrinsic damping if you are in the really highly disordered regime, then again the color will now only depend by the Fabry-Peyroux cavity, so by the dielectric layer that you have below. Yeah? So these here are still computational results. I don't have too much time to go into it, but what it basically shows you is here 4 different materials here. This is the thickness of the underlying Fabry-Peyroux cavity, and you see the color, so the far field response doesn't depend on the material at all anymore. It only depends on the Fabry-Pérot cavity. And like this is now quite interesting because this means you can also use combination of different materials. You know, because of course locally, the like near field that you get, that of course depends very much on the material, right? So silver has a much higher local field enhancement than gold, or than palladium, or than platinum. But you can use this effect of disorder now to basically controllably get energy in the spectral regime that you want to your surface. The actual material of your colloid only plays a like secondary role, and then use the local material for the function that you want. So for example, if you work in photocatalysis, you could think of a mixture of silver particles and platinum particles, where the silver particles would give you the field enhancement, the platinum particles would be used for the photocatalytic conversion that you want to address, but the overall bandwidth of light harvesting is only dependent on the cavity underneath. So we've published this already a while ago. These are like experimental results here. So you see highly disordered deposition of clusters under our dielectric layer. These are 5 different thicknesses here, and 4 different materials. And as you see, the color looks the same. So this is just like a very simple example to show you that this critical coupling process is actually something that can be exploited in quite surprising ways. And again, the only key here is that we use the dielectric spacer layer to basically change the lifetime, if you wish, of one of these colors to take it out of the critical coupling condition, and hence change the optical appearance. And I should just say, obviously, the opposite also works. Right? So this is shown for harvesting, so this obviously also works very well for actually getting light out of a material, right? And that is used in nature all of the time, right? Insects, I think this is a firefly, you know, how do they get the light over such a broad wavelength range actually out of them, right? We have a high index material, right? You would expect lots of total internal reflection. It is because their surface structure is highly random, right? If you want to get light, that's a typical problem with light-emitting diodes, right? For example, out of high index material, you have to fight total internal reflection, right? So you can put obviously a grating structure on it. That's then very narrowband, but the more and more random you become, the broader the wavelength over which you emit, right? So this is, well, again, this is more or less trivial, but it's just the opposite process that is at work also via this critical coupling. Yeah. So this was, you know, just here also a very simple experiment. You have a high index prism. You put a disordered array of silver particles on top, and this way you can get much more light out of it above the angle of total internal reflection. So you might say, okay, that's not very useful, but it actually quite is, because you know, if you now, for example, take just a commercial solar cell. So this here is an example of a commercial gallium nitride solar cell, and you want to enhance its external quantum efficiency, you know, only by a few per cent, not too much. We got a total enhancement of 1.65. All you need to do is put a highly disordered array of silver particles on it, and you enhance the total external quantum efficiency. And the nice part is, you know, this is not a very invasive process. I don't have time, and that's also not probably so interesting for the audience here to go into this. But basically, the electrical characteristics, at least in our experiments, of this solar cell basically did not change at all. So if we look at the voltage versus current curve of the naked cell, so to speak, and the cell with this silver colloid ray on it, basically nothing changed, but the light extraction efficiency did. Okay, so this one example, very, very simple example where critical coupling is at play, yeah, in highly disordered arrays. Okay, so now for my remaining time, I want to show you how we can now actually engineer this. Okay, so how we can engineer it to the wavelength where we want this to occur, and I'm going to show you two applications. One is an application in energy conversion, and the other one is an application in sensing in the mid-infrared. Okay, and like the concept in both is the same. We will now not use the disordered colloids that I showed in my introduction, but we will now use this little ellipses where we have really good control over that coupling factor to the outside. Yeah? And again, the like basic concept is we start with a mode that has zero coupling. Yeah? So ellipses like this. Dark mode, dipole moment up, dipole moment down. We change the symmetry a bit, so we couple a tiny bit, then we change it more and more and more. We like couple more and more and more, and we want to match this now to the intrinsic absorption that we have in them. Okay? And the first example that I'm going to show you now is one in the context of photocatalysis. So like what we want to do here is we like want to use the energy from the photons to get absorbed in our material, generate electron-hole pairs, and then use this for some sort of chemical conversion. Yeah? And like since we are like not chemists, the easiest part, the easiest way to do that is using a very well-known material, and that's in this case titanium dioxide. Okay, so that's one of the kind of standard materials for photocatalysis. It has a band gap in the UV, so it doesn't usually absorb. But the like interesting part is that you can very easily generate oxygen vacancy centers in there, either via etching or via UV illumination, so basically defects, in order to generate absorption in the visible. And that's now really interesting for us because that gives us now a like second knob, so to speak. It like gives us a control knob now to also actually control the extinction of the material, so the imaginary part of the refractive index. So we now have one knob. If we now like nanostructure this, yeah, via the angle of our ellipses, we can change the coupling to our light beam, yeah, or to our plane wave, and via basically generating defects in the material itself, in the titanium dioxide itself, we can change its absorption. So we have a control knob for both parts of the critical coupling, for the absorption and for the coupling to the outside. And like what we like demonstrate here is that if these two coincide, so if the extinction is the same, the absorption, so the extinction coefficient of the material equals the coupling constant to the outside, then indeed we have the largest amount of energy conversion. So now how like do we model? So how do we observe energy conversion? So this was done in collaboration with Emiliano Cortez's group, like at LMU. In like a rather like simple way, we like immerse everything in silver salt solution, and we use the charge carriers generated in the titanium dioxide to reduce the silver salt and then basically nucleate small silver nanoclusters. Okay, this is obviously not an extremely, well, it's not a system where we actually can very well quantify the energy conversion rates, but for our purpose of showing that this critical coupling works, I think it worked actually quite well. And like I will now show you now the examples. So yeah, so I will get back to like all of this in just a moment. But so basically what we do is, so we have 3 different films of titanium dioxide with different amount of concentration of these vacancy centers, okay? Very few vacancy centers, so it almost looks transparent. Yeah, if it was like a thin film of just pristine titanium dioxide band gap in the UV, it would look completely transparent. Then we have one which we call M, so that's a medium amount of vacancy centers. You see it gets a little bit darker, and then here high, a large amount of vacancy centers. Okay, so basically if you wish 3 different extinction coefficients, 3 different settings of my extinction control knob of my material. And now we like nanostructure it into our little ellipses here. Okay, the size of the ellipse determines the wavelength that we want to tune to, which in our case was helium neon laser, and the angle between these ellipses. That's our like second knob. That's the coupling strength to the outside. Yeah, so you can see here these plots here for these three materials show the absorption of. So this is a computer simulation, obviously, of the titanium dioxide versus like tilting angle. Yeah, so at zero tilting angle, no like absorption because we have these dark modes, and then as we start to tilt, you see the mode appear here for the low loss, for the medium loss system, and here you see for the high loss system, we like already have such a large amount of vacancy centers in there that we basically don't see the mode at all anymore. Yeah? So it's these two that we are going to concentrate on now. Yeah? And then, like as I said, so by like scaling the whole thing, we can now make sure that when we change our angle and hence change the coupling constant, we can offset the spectral shift that we get so that we are always at the wavelength that we want. Okay, the helium neon laser wavelength. Okay, and then we do our experiment. Yeah, so we now basically have our two different types of titanium dioxide, yeah, little like pixelated areas where we have different angles between these ellipses, and with a dark field microscope and some like automated estimation of the scattering that we get due to the nucleation of these silver particles, we now basically sum up, yeah, how much silver do we nucleate, so how much energy did get converted, that's on this axis here, versus the tilting angle, so versus the control knob for the coupling to our surface for the two different titanium dioxides in question. Okay, the low loss one, which is shown here in pink, and the medium loss one, which is shown in blue. Again, the like high loss one we could not use because we have so many vacancy centers in there that we actually don't have a nice optical mode at all anymore. So there are two things of note here. Yeah? So the first thing, and that's maybe like if you don't come from the nanophotonics area, the most surprising, well, the like low loss one wins. Yeah? So the low loss material is actually able to produce more silver clusters via energy conversion than the high loss material, right? And I mean, like obviously it should be the like other way around, right? If you have like a thin film of a photocatalytic material, the thin film with the largest amount of extinction, so highest amount of imaginary refractive index, highest amount of intrinsic absorption should win. So here it is the other way around. And like that alone is interesting because that can, you know, open up new classes of materials that actually intrinsically don't have a large amount of absorption to photocatalysis, because you can play with this concept of critical coupling instead. And the next thing is the critical coupling, yeah? So you see there is an angle actually where the conversion rate is the largest, and it's very pronounced here for our low loss material, a little bit less pronounced because we're kind of just at the outside here, but it's around 15, 16 degrees for our other material here. So if you now actually do your computation, so you know from the amount of vacancy centers that you have created in your titanium dioxide what the extinction is. Okay, so we have here the extinction coefficient of our material. This one here, again in red, is our low loss material. This one here is our medium loss material. And you plot this against the tilting angle, and again the like tilting angle controls the knob of coupling strength to the outside. When both of them equal, we have the critical coupling, which is this curve here, this yellow curve here. And you see, well, we have two crossover points for our two materials. And if we now plot underneath, where do we have the largest conversion, the like largest amount of silver cluster deposition, then you like nicely see, well, it almost perfectly coincides. Yeah? So it's this critical coupling that has basically now allowed us to take a material that's intrinsically low loss and increase its effective absorption, obviously here for like something quite rather boring, right? Generation of clusters of silver, right? But like you could think about using this, you know, for ammonia reduction, you know, hydrogen production, and so on and so forth. Yeah. So this is really kind of like the main like message, you know, that like kind of like playing with this critical coupling concept, you know, you are now able to extend your portfolio of materials for energy conversion to materials that have intrinsically low extinction. If you then at the same time nanostructure your material actually tailored to that extinction coefficient, you like want to nanostructure it, yeah, so that again for the photonics people, for the few photonics people in the room, that its radiative quality factor basically, yeah, equals the extinction that you have, so that you get this critical coupling. Yeah, so we summarized all of this recently in I think quite a nice chemical reviews article headed by Amy Cortez. Okay, so now like in my last few like minutes, I will just show you that like also the like same concept you can use obviously also for sensing. So here we were after sensing in the mid-infrared, so SIRA, yeah, so surface-enhanced infrared absorption spectroscopy. We are now dealing with wavelengths, you know, of like a couple of microns. So fabrication is far less critical than at visible frequencies, right, where you need to use electron beam lithography, and also like in order to use a little bit of different structures, but exactly the like same concept, we use 3D direct laser writing to basically make little pillars, polymer pillars. Yeah, so you have a block of, I should maybe very quickly explain how this works, like it's very like simple. So you have a block of polymer, and you basically polymerize it via 2-photon absorption with a laser beam, and this way you can make nice three-dimensional structures. Okay, and we use the same concept now again to get control over our coupling strength to the outside. So we start with a mode. Yeah. Oh, I should have said, and then we coat everything with gold. Yeah. We start with a mode that's intrinsically dark in the wavelength region that we want, and like this is basically just a rod pointing up. And we excite basically, again for the photonics people here, the monopole mode. Yeah? So like a quarter wave resonance we would excite, but it's a dark mode since it doesn't have a dipole moment. And we break the symmetry now by basically tilting this rod a little bit. Yeah? So rather than being like perfectly up, we have now a tilting angle here, which now leads then also to a dipole moment. Yeah? So just as with my two ellipses before that are slightly tilt, what my control knob here now is basically the opening angle of this rod here. Yeah? So you see some examples here. Yeah? 4 degrees, 12 degrees, 22 degrees. In this way again, we have our knob now to control how much coupling do we get to the outside, yeah, and then we can also control the spectral region where this happens again via a simple scaling in size. Okay, and then we make like little like pixel-like arrays. You see like one example here now when we put this under a mid-infrared quantum cascade laser microscope. So this is a Spero. Okay, so all of these different arrays that you see here, yeah, have now basically a different size of this structure, so they are resonant at different wavelengths, and again the like sharpness of these resonances I can then control via the opening angle. Yeah? And if you then sweep your quantum cascade laser, you know, you will see all of these different pixel arrays like light up. Yeah? So here we like swept from about 5 microns to about 10 microns, and you see we have some patches resonant here. Yeah? And now for like a simple sensing experiment, we coated everything with PMMA, and we looked at the sensing performance. And what we like expected, of course, was just as before, that on the critical coupling condition, we expected that we see the largest change in signal, so the largest change in SIRA signal. Yeah? And again, the way that we get into the critical coupling condition here is via changing this angle here. Yeah? So we tune the size of our rods to the vibrational resonance of PMMA of interest, and then we go into a regime where we are undercoupled, critically coupled, or overcoupled by simply changing this angle. And the surprising result, and like that we don't really like understand yet, is that we get the largest amount of differential signal. Yeah? So the largest signature of PMMA actually in either the undercoupled regime or in the overcoupled regime, but actually not in the critical coupling one. So that's something that we don't understand yet. Yeah, but I think it's something like interesting because, like, of course, you know, the like same concept is at play. So, like at critical coupling, you get most of your mid-infrared radiation actually to the surface structure. So you would expect to have the largest amount of field enhancement then, but actually the differential signal that you then get due to the absorption of your molecule on it, and again in like this case it's a very thin layer of PMMA, is basically almost absent. Yeah, so that's something that we need to look into more. Yeah, but like I think it like kind of underlines the like basic message that for all of the applications in using cleverly designed nanostructures for, you know, for sensing, for energy conversion, it's not just spectral control that matters. You know, obviously you like want to match the wavelength region where you want to sense or where you want to convert energy. What like also matters is that you need to finely tune how strong do you actually couple to the outside, yeah? Because it has profound implications of the strength of your like overall readout system. Yeah, I should like just say if you want to like combine something like that with like electronics, so with electrical control, this is my like last slide, and like other way of breaking symmetry to actually generating these modes with only a small amount of dipole moment. It does not necessarily need to be a change in geometry, like tilting ellipses or so. It can also be a change in like permittivity. Yeah, so you know, if you take a asymmetric system, yeah, rather than changing the symmetry of one of the elements to get your dipole moment, obviously you could also just change the permittivity of one of them. And that might be interesting, for example, if you want to translate these concepts to 2D materials, where you could then think about some sort of electrical gating of actually introducing these modes. Okay, so I have to thank like a large amount of people. Like I just want to highlight here Emiliano Cortes for all the chemistry work, Andreas Tittel for really a large body of work on these particular resonances called quasi-bound states in the continuum. I think I never said the name here, but these resonances where you break the symmetry to get that very good control are known as quasi-bound states in the continuum. All the students that have worked on it, and you, thank you for your attention.
Thank you very much, Stefan, for this very nice talk. And so we have a little bit of time for discussion. So we're going to start here.
Thank you very much for a very nice talk. I just have one question. Is there any reason why you choose Sierra with different structure, nanostructure, and not the previous one, and for example, SARS effect?
No, like it was like mainly because we wanted to do a demonstration in the mid-infrared, and the particular project in question wanted to use 3D direct laser writing. So no, it was not, no. Yeah.
We had one here.
Yeah, just a technical question on this photo that you show on the third part of. I'm here. Yeah.
Yep.
And
sorry. yeah, I see a microphone here. Hello, yeah.
Yeah. So the photos that you show on the nano antenna. I'm doing a bit of nano fabrication, and I know that it's really difficult to get an angle in the vertical direction. So. How are you doing this?
So like this is kind of the, well, almost standard commercial system, the like nanoscribe, 3D direct laser writer used for that. Obviously, if you wanted to do this for visible frequencies, then it would be like much more difficult than to actually do an edge. You know, here the like main problem here is actually how do you get a nice conformal coating of gold.
Okay.
Onto these, yeah, but like the like actual, yeah, I mean, so we had some problems at the beginning also. You know, if you have a high like aspect ratio, sometimes the pillars fall over if they're perfectly vertical. So it is an issue, but it's not.
Okay.
With enough trials, it's actually not that critical.
We have another question over there.
So I'm wondering, in the first part with the quasi-bound, with the bound states, and for the critical coupling condition, what is the role of the disorder? So the strength of the disorder. So let's say we take a perfectly periodic structure and we start perturbing it, changing the position. At what point are we going to see the effect?
Yeah, yeah. I don't have the slide actually in here yet, but yeah, that's a very good point. Yeah, I don't have it here. So we investigated that a little bit. The short answer is you need a very, very large amount of disorder. Yeah. So so we used cluster deposition from vacuum to generate our highly disordered silver clusters. And what you basically see is that because this simple example here, this was all about color generation, that basically the chromaticity, so the spectral sharpness of this reflection band depends very much on the amount of disorder. So we didn't quantify this. I know what I'm saying is hand wavy, but we did 5 different, to the eye at least, amounts of disorder, and you could then nicely see, so everything was tuned to the green, how first a very kind of almost desaturated grayish green appears, and then as your disorder gets more and more and more, then you start to become more and more chromatic, basically. Yeah. So if you look at this quite old paper now, it has the it has that example in there.
Ivan, last one.
Yes, I was wondering in the field of solar cells. I mean, is it really at the moment? So you're working on the collection of electromagnetic energy in solar cells, but at the moment, is it really the dominating, the limiting factor? I mean, the collection of electromagnetic energy from a solar cell?
No, not for that.
It seemed to me that there was more an issue with the collection of hot electrons,
sure.
energy.
Yeah.
So what is the spirit of this approach, or is it for another kind of application? Maybe not strictly speaking for the regular type of solar cells that we have in mind?
No. So we are actually here not after solar cells at all. We are after photocatalysis, and here actually it's and that actually is very good, that you made this point that the collection of charge carriers is a problem. I mean, that's a large problem in many of the standard materials that get investigated for CO2 reduction or for hydrogen conversion, for example, because you always need to fight the the length scale over which the free carriers will just thermalize, right? Which of course depends on the extinction coefficient also of your sample. So with these kind of tricks, right, where you widen the pool of materials available, you can now actually go to materials where the electronic properties might be more favorable for charge carrier collection. Many of them don't absorb a lot, but then you can counteract that at least a little bit if you play with these critical coupling ideas here to get at least as much energy as possible into your low absorbing system. And as we have at least shown here, so for this particular example, they are our systems where then actually the low absorbing material wins.
So we'll have to stop here. If you have further questions, so you can catch Stefan during the coffee break. Thank you again, Stefan, for your talk.
Thank you.